We are in Unit 2, Earth Processes. Now, you've already started your flashcards, which is a good thing, because, piece of wisdom, you will never finish if you don't start, right? Okay, so how many individual tectonic plates can you count on this world map? And your notes, you can see at the very top, it says that there are really over 100 different plates. But this picture, didn't tell you that many. So I don't want to see the number 100 in that space. I want to see how many you counted in that space, okay? And you should have gotten somewhere upwards of 25 to 30 or something like that. Okay, so we're going to be studying tectonic processes like earthquakes and seismic waves and weathering, erosion, and sediment. How does all that stuff get into the ocean, right? And then tides and ocean currents. So this is three-part notes. That's why it's so long. So we're only going to do part 1 today. All right, so the first part is you have to label these diagrams in your notes. So you'll see the first pizza cake pie looking diagram there. That is this with the missing pieces, so make sure that you fill those in. Ocean, crust, lithosphere, mantle, outer core, inner core, the whole core, both the outer core and the inner core, something called a Gutenberg discontinuity layer, and then the asthenosphere, just like it's spelled, as-then-o-sphere, asthenosphere. May look like a weird word, long word, but all right. So one of the parts of this unit is you have to describe the structure of the Earth limited to the crust, both oceanic and continental. So here's continental crust, here's oceanic crust. You can see the difference. Oceanic crust is much thinner than continental crust. Continental shelf is the part in the ocean that rises to meet the land. Okay? And then the mantle, and then the core. So if you were to describe the Earth in 3 parts, you'd say crust, mantle, core. Just like that. Just like it says here. But of course, and this isn't even that complete. This is missing some pieces of the diagram. But for this level of course, we don't have to know those other pieces, which is good, okay? So try to finish up as much as you can right now. And if you miss anything, you will have to come back to that on your own, okay? All right, so 10 more seconds on this slide, labeling. Take a picture with your cell phone. 10 seconds, 9, 8, all of you scrambling to get your cell phone. 7, 6, hurry up. 5, 4, 3, 2, 1. Time to change. All right. So on page 2, slide 3, underneath that last diagram there, there's a thought question, and you have to put the answer to these thought questions down. Now, some of you are leaving them blank on your last sets of notes, and I have to take 5 points off for every question blank. It's 2 points off for every other blank, but 5 questions for questions. 5 points for questions. So here's the thought. What are the chances that these 2 continents, South America and Africa, just happened to fit together like puzzle pieces? Very slim, right? So what forces could be responsible for the movement of such large pieces of Earth's crust? Now, I did describe this on the board last week when we were designing our experiment to determine the rate of widening of the Atlantic Ocean. So I think you know the answer to that, all right? So we're going to go back in history a little bit. We're going to do a little history. and we're going to discuss Abraham Ortelius. Now, this guy was a Dutch cartographer. A cartographer is a map maker, and he noticed how the continents fit together like puzzles. So he proposed that North America and South America had been separated long ago from Europe and Africa by earthquakes and floods. He had no evidence, but it was a guess, okay? All right. Earthquakes and floods. So he published this map, slide 5, bottom of the page. There's a question there. He published this world map in 1570. So the question is, what does the map show to help Ortelius's theory? Well, it's obviously showing something going on here and here. And if you looked carefully, you'd even see that Spain he has fitting perfectly into, and we know that this is not the exact shape of the eastern seaboard, okay? Here's Florida, that's where you are right there. And that's not the exact shape of South America. They hadn't explored much of that yet. They didn't even have the shape of, actually India is over here. So this is California, Southern California, right, okay. So Australia was kind of off there. New Zealand's there, but you can barely see. Anyway, my point is, a lot of things were off. And he probably changed some of the coastlines to fit his theory. That's because, people didn't think too much about scientific, ethical issues with science back then. So now we're going to go ahead almost like 500 years, 400 years or so, page 3 now. It's Alfred Wegener. Alfred Wegener is probably the most popular scientist in this area, because he was the first scientist to actually use real scientific data to back up his theory. So he was actually using facts to back up his theory, okay? German scientist, 1912. So he quoted, "The Earth's continents had once been joined as a single landmass that broke apart and sent the continents adrift." And he called that supercontinent, and you all know Pangaea, for all Earth. It's a Greek word for all Earth. So if you start back at the beginning of this, you could see how over the tens of millions of years, hundreds of millions, or 250 million years ago, all the plates are moving in this direction. The yellow is the African plate. So let's go, start 150 million years ago. It was actually more than that, but 250 million years ago is more when Pangaea was around. You just watch one spot and you can see how they're moving. And those little lines show the movement of the plate. Wherever they're pointing, that's the way the plate is moving. So watch it one more time. You see India goes all the way down here from touching Antarctica all the way up to crash into southern Asia and make the Himalayan mountains. And the African plate is crashing into southern Europe to make the Alps mountains. Italy is actually part of the African plate. And so that's why the Alps mountains are where the top of Italy is, okay? And so you can, and the Andes mountains are here. These mountains were made long ago. These mountains, the Appalachian Mountains that are ones close to us, were made long before that. So it's all, you could study that diagram, that animation, for a very long time and determine what it all means. But okay, so here's his evidence. The first piece of evidence for Alfred Wegener was rock formations. Okay, and there's a question for here as well. There was a question on the last animation too. I hope you got that. So rocks in the Appalachian Mountains are similar to those in Europe and Greenland, which is where I just left off on the last slide. So when these were together, the Appalachian Mountains were created. Now the Appalachian Mountains are some of the oldest mountains in the world. They're older than, any rounded mountain chain is older than any jagged mountain chain. And you can see how North America used to butt up against Africa. So Florida, the bedrock deep down below us, not the stuff on top that was made later, used to be part of South America and Africa until great forces, starts with a C, it's a long word. Hot rises, cold sinks, you got that from before, right? Okay. Convection currents, that's what it is. Move these apart. So the question here is, the Appalachian Mountains are only a 9-hour drive from Boca Raton. They're not very tall, and they are very old. Why do you think the Appalachian Mountains are both not tall and some of the oldest in the world? So you have to answer that on, your own time. Okay, that was the first piece of evidence of Alfred Wegener. The second was fossils. Oh, we didn't get there yet. Hold on. That was the next slide. Okay, yeah. Anyway, so this is an example of the rock layers in South America and Africa and how they are virtually similar, even though they're separated by the Atlantic Ocean now. There we go, evidence from fossils. This is one of my favorite diagrams, and I'll show you why in a moment. So fossils of species like the Mesosaurus, this guy here, could not have crossed, this organism could not have crossed such a wide expanse of salt water. It didn't live in salt water. So it could have done maybe a short expanse, but not such a wide expanse. Nonetheless, fossils have been found on both of these continents, even though they're miles, thousands of miles across now. Same with this one, both of these continents. Same with this creature. Madagascar, Africa, India, Antarctica. Yes, Antarctica. And then this plant called Glossopteris on all of these continents. Fossils of this plant are found on all these continents. It doesn't exist anymore, it's an extinct species, but how did that happen? I mean, Antarctica must have been at a higher latitude on the Earth to receive enough light energy from the sun for these plants and other animals to live there at one time. So Antarctica moved down, South America moved like this, Africa moved up, India moved up this way, Australia turned and spun and went this way. So the fossils helped Alfred Wegener determine his theory. All right, the third one is climate evidence, and we're going to go back to that Glossopteris plant again. So these are actual fossils from that plant found in different parts, different continents. So at one time, these land masses must have been together in a more temperate climate. That means closer to the equator. Again, questions for that one. Okay, we're on the next page. And the questions you can do later, don't worry about that. Just don't turn them in. Doing the questions later helps you go back to the notes and look over them and study them. All right. And paleomagnetism is the final piece, 4 pieces that Alfred Wegener used that the other scientists did not use. So, again, we learned that the convection currents underneath the magma, underneath the crust, are turning like this, pushing apart these plates. This is called a divergent plate boundary. Diverge means to come apart. Converge or convergent means to come together, right? So, so about every 100,000 years, and we're going to watch a video on this, about every 100,000 years, the Earth's magnetic poles flip. Now, I don't mean that the Earth flips physically. Just the attractive forces that make the North Pole, the magnetic North Pole, north and the magnetic south pole south, for some reason that we're going to learn in the video we're going to watch, actually flip. And we're overdue for one right now, actually. It's been more than that long since the last one. And there's some signs that it is flipping, starting to flip. Major airports have had to repaint their north arrow on the runways. So pilots, when they're coming in, they can determine which way is north, and depending upon the wind and stuff like that, as their instruments go out. So they had to repaint that because of the changing North Pole. You know, the magnetic North Pole is not at the geographic North Pole anymore, where Santa Claus lives. It's actually in like Scandinavia. So here's the geographic North Pole, and here's where the geomagnetic North Pole is supposed to be. It's actually over here now. So when it flips, the new magma coming up orients itself in a north-south direction based upon, when it cools, based upon the magnetic pole of the Earth, okay? And so every 100,000, when they drill down into the seabed and pull up samples, core samples, they can see that this was north-south, this was south-north. This was north-south, this was south-north. And so that's showing that it's moving apart. Paleomagnetism. All right, Harry H. Hess, the 3H guy. Slide 13. He's a professor at Princeton University, 1962. He wrote a book, The History of Ocean Basins. And his theory, of course, because he was probably, he probably read Alfred Wegener's and studied Alfred Wegener's stuff, like other geology professors at the time and today do. Seafloor spreading. So he came up with seafloor spreading. So let's see what's going on under the crust to cause this seafloor spreading to occur. And this is an example of the mid-ocean ridge, the mid-Atlantic ridge, but there are ridges like this all over the planet, not just in the Atlantic Ocean. So, and of course, you can see in your notes that the answer is convection currents, right? So hot magma rises and moves to the plates above it in measure. As hot magma rises, it moves to the plates above in. That's a typo. That's supposed to say in measurable ways. Fix that in your notes, okay? All right, so cutaway of the Earth, right? And so you can see hot heats up, rises, cools. Heats up, rises, cools. So the red is heated, rising, and then blue is cooling. And that's happening all over the planet, driving those plates from the very first slide that you saw in the notes to move the way they do. Sometimes they move a lot, sometimes they move a little. Those powerful convection currents that move the plates apart, in some places diverge, like I said before, in other places converge. So you can see, we'll wait till the animation starts over again because it's pretty, I like this one. So you see them going, rising, hitting the surface, heating from the core, rising up. It's not smoke, it's magma, hitting the crust, bowing out like this. It's got to go somewhere, right? New magma is rising, making seafloor. And then over at the sides, it's pushing the old crust back into the earth again and recycling it. So let's start it over because this is a really good animation. So the magma is rising, weakening that spot where it hits its hottest, making new seafloor. And over here now, it pushes that back under the continental crust because this is lighter and thinner, and it recycles it, melts it back down again, brings it to the core, and the whole process starts over again. It's quite amazing. Now, of course, this is a theory. This is the theory of plate tectonics. Theories mean that when you find new facts, right, the theory changes. Theories are living things that change and evolve based upon new evidence. Can we go down inside there and watch this happen? No, we have to use all the evidence that we can gather at the moment. Okay, that's why it's a theory. Okay. So, next slide, 17, towards the bottom of page 4. We're going to talk about the different kinds of boundaries. So divergent boundaries are the ones we already said that move apart, like we've been studying here already, like in a mid-ocean ridge. So the plates separate due to convection currents in the middle. It stretches the thin rock, creates tension, there are earthquakes, and new crust is created and moving out. Convergent boundaries are the opposite. This is when plates collide. So you've got continental crust and oceanic crust coming together. And so you get, it squeezes and compresses the rock. Rocks are thrust up over one another. You get mountains, sea mounts, and other structure of a trench here in the ocean. It could be a deep trench right there. And lots of earthquakes, okay? It'll actually scrape off pieces of land and move them up onto the land, many, many miles in. Sometimes we have them here in North America, California, for example. And this is called a subduction zone. It subducts. One subducts under the other, like this, and that pushes up mountains and volcanoes too. Subduction zone, happening off the coast of South America. That's where the Andes Mountains are, right along the coast, because South America is hitting the Pacific Plate. So here's India coming up and crashing into southern Asia, pushing up the Himalayan mountains, the tallest mountain chain in the world. 10 million years, 10 million years, 10 million years, 10 million years, like that, okay? C are transform boundaries, middle of the page. So here is where they slide past one another, like this. Transform fault. So here you've got a divergent boundary. These are moving apart, but because this divergent boundary doesn't meet up with this one, it used to, but now this one is sliding as it moves. As these move apart, it slides like this. And so they're rubbing like that. Another example is the San Andreas Fault in California. And the rocks are broken as they grind past one another, and they get locked up and create lots of earthquakes. Grind past one another. Okay. Oh, there was an animation there. Sorry. Didn't know that. Watch it one more time. I think. It doesn't want to play again. Okay, so now we're on divergent features. These are the features at a divergent plate boundary. So you're going to get hydrothermal vents, abyssal plains, volcanoes, earthquakes, creating new crust. These are all the things, and any earthquake that happens underwater can cause a tsunami. Do not confuse a tsunami with a tidal wave. We'll get to that in another part of the notes. A lot of people say a tidal wave is a tsunami. Not the tidal. Has to do with the tides. Totally different. So yes, and they do. A lot of you said you were going to put sensors in the water. You were spot on with that, because there are remote offshore seismic stations that monitor activities, that when a signal comes, they send that signal out via radio waves, and we can get a warning that there's a tsunami coming, okay? If there's an underwater eruption. And we're going to learn about hydrothermal vents more in the future, but for now, an abyssal plain is this. It's a vast area of virtually nothing but flat ocean bottom. Obviously, you know what a volcano is, earthquakes, and creating that new crust. You know those things. Okay, so we're gonna watch a little video right now, I think.
This is the moment that a volcano erupts underneath the sea. Although relatively little is known about them, it's believed there are over 1 million submarine volcanoes, largely located along the mid-Atlantic ridge. A spectacular sight from above the water. Here's a rare glimpse of an eruption beneath the waves. These volcanoes are responsible for producing 75% of the Earth's magma. Underwater volcanoes are understood to work like their counterparts on dry land. They form towering mountains submerged well below sea level. Some reported to rise as much as 10,000 feet above the seabed. While it's relatively rare to see, these eruptions can also create new islands above the water. On November 14, 1963, a trawler sailing just south of Iceland noticed a plume of smoke billowing from the sea. Thinking it was a fire on board another ship, they travelled towards what was, in fact, an underwater volcano erupting and witnessed the birth of a new island. It was named Surtsey, after fire giants of Norse mythology.
1963, no close approach to the crater seemed possible. It belched lava at the rate of 500,000 tons an hour. Ships and planes were warned to give it a wide berth. Volcanic islands like it had been thrown up before in recent times, but not for 1,000 years has one of this magnitude survived. The lava which once spilled over the yellow rim still bubbles angrily. The liquid lake is 300 feet below now, but jets of bright red lava still spurt up, and the fumes are intense. The mountains thrown up from the sea less than a year and a half ago look as though they've weathered the passage of centuries. And the dust piled up round the plane wheels in our absence showed how swiftly the pattern of nature is still changing here.
Today, the island of Surtsey is a UNESCO World Heritage Site, and the only people allowed to set foot on it are the scientists studying the ecosystem and geology of this unspoiled isle. It's thought that Iceland itself was created in this way by underwater volcanoes millions of years ago. So while it may be rare to see one erupt, these submarine volcanoes have a big part to play in shaping the world above water.
Okay. Next. Okay, so now we're on convergent features. Okay, so there were some questions there about that video. Convergent features, trenches, volcanoes, earthquakes. When they come together, you're going to get tsunamis even more with these type of boundaries, okay? Release, it's energy transfer from the rock to the water. That's, of course, this is a vast exaggeration for the purpose of the video, not the diagram. Thank you. Okay, but when it comes to the shore and starts to trip up on the shoreline, it will rise up like that. All right, and of course, loss of crust, because this crust will get recycled back down into the magma, into the hot part. So that's convergent, coming together.
A tragic scene. Entire cities flooded, entire towns inundated, an unending stream of floating debris. Buildings, cars, people swept away in an unstoppable wave. It's a brutal reminder tsunamis are dangerous and unpredictable. But what causes these giant waves and what can be done to minimize their impact? Tsunamis can strike with little warning because they're usually triggered by a sudden displacement of ocean water, like volcanic eruptions, landslides, meteorites, or the most common culprit, earthquakes. In the deep ocean, a typical tsunami wave is barely noticeable and poses little threat. But the waves can spread out thousands of miles, rolling across the ocean at speeds up to 600 miles per hour. As the rolling water reaches the shoreline, the wave's friction against the shallower floor slows it down and raises its height. By the time it reaches the shore, the wave can be as tall as 100 feet. Unlike ordinary waves, a tsunami wave doesn't crest and break. Instead, it moves forward like a solid wall of water that crashes over the coastline, obliterating almost everything in its path. And just when you think the danger is over, it recedes, dragging everything back to the ocean. Tsunamis have multiple waves, which can continue to hit the shore for several hours, causing even more destruction. The word tsunami originates from Japan, a country that sits on a geographic location that makes it an easy target for these natural disasters. In 2011, it was struck by a tsunami that claimed nearly 16,000 lives. But the deadliest tsunami in history is believed to be the Indian Ocean tsunami of 2004. The U.S. Geological Survey estimated that tsunami released the energy equivalent of 23,000 Hiroshima-type atomic bombs. An earthquake created an estimated 600-mile rupture on the ocean floor. This caused the tsunami to form and then travel at the speed of a jetliner, reaching over 11 countries, traveling over 3,000 miles, killing more than 220,000 people. Because they can strike so quickly with such deadly force, tsunami warning centers around the globe are on constant alert, monitoring underwater earthquakes large enough to trigger massive waves. Their ultimate goal is to alert vulnerable coastlines and give residents time to seek higher ground before a tsunami hits.
So, back to here. We are on transform. Okay, the bottom of page 6. So at transform boundaries, you're going to get earthquakes and fault lines forming. There are mountain ranges that also form, or oceanic ridge crest it's called. So earthquakes and fault lines, turn the page.
From above, the planet appears eerily still. But every mountain range and every chasm on its face is a scar, with many telling a story of when the Earth rumbled to life. Earthquakes occur around the world. They've been recorded on all 7 continents, but most quakes take place in just 3 regions. The Mid-Atlantic Ridge, an underwater line that runs down the Atlantic Ocean, the Alpine Belt, which stretches from the Mediterranean to Southeast Asia, and the Circum-Pacific Belt, which traces along the edges of the Pacific Ocean and is where about 80% of all earthquakes occur. These areas experience the most earthquakes due to what lies beneath the surface. Earthquakes are the result of pressure, specifically pressure caused by extreme stress in the Earth's crust. That stress can be caused by volcanic activity or even man-made activities in certain areas. However, most earthquake-inducing stress is caused by the movement of tectonic plates. Tectonic plates are constantly moving, either against, away, along, or underneath each other. But sometimes their edges may catch and stick. The plates, however, continue to move, or at least attempt to. Energy from this attempted movement builds around the edge's sticking point, creating immense pressure until the edges are forced to let go and the plates slip. This causes a sudden and powerful release of energy. so powerful that it breaks the Earth's crust. This fracturing emits shock waves through the ground and causes intense vibrations, or quakes. In fact, the world's most earthquake-prone regions are where the most geologically active plates meet. Earthquakes, or any seismic activity, are recorded by seismographs. When the ground shakes, seismographs oscillate, drawing a jagged line to reflect this movement. The more extreme the earthquake, the greater the height of the jagged line. These recorded motions are then used to measure the earthquake's strength, or magnitude. While several scales of magnitude exist, the one seismologists prefer is the moment magnitude scale. It has no upper limit, and it measures earthquakes logarithmically. This means that each magnitude on its scale is 10 times greater than the one before it. Unlike the now rarely used Richter scale, the moment magnitude scale can be applied globally and can measure quakes of the highest magnitudes. The largest recorded earthquake occurred near Valdivia, Chile in 1960. Nestled within the Circum-Pacific Belt, the Valdivia earthquake was the most powerful in a series of quakes that struck the region, measuring at a magnitude of about 9.5. In addition to causing devastating tremors on land, the earthquake also generated a deadly tsunami reaching up to 80 feet high. The tsunami raced across the Pacific Ocean, hitting faraway countries like the Philippines and Japan. In fact, data from seismographs showed that the shock waves emitted by the Valdivia earthquake continued to shake the entire planet for days. Some earthquake-prone areas have adapted various ways to protect their communities. Buildings and bridges are designed to sway rather than break when an earthquake occurs. The public is educated on how to protect themselves during a seismic event, and government officials enact drills to ensure the protection of their people. Earthquakes can leave behind incredible devastation. But these same forces have also created magnificent features, with each adding character to a planet so unique.
Okay. Next slide, we're almost done. 27. Okay, which is right there in the middle of your page, on page 7. So make sure you fill in the hydrothermal vent information or formation, which is, on your notes. Understand that the effects of the hydrothermal vent plume, that's the next slide. Yeah, okay. So you're just labeling this right now. So you're labeling cold ocean water seeps through cracks in the crust. So you've got magma close to the surface, which is heating that cold water. And you know that when you heat water, its solubility of solids goes up. So it's going to dissolve sodium, calcium, potassium, sulfate, magnesium, all that stuff. It's going to dissolve it and move it around. And so when it comes out, as the hot rises, okay, so it's cool, it's sinking, it's heating, it's rising, it's absorbing all of those dissolved solids. It plumes it out into this smoke plume called a black smoker, a hydrothermal vent, and a couple other names. And so it makes this entire ecosystem down there that animals that don't live anywhere else in the world only live right around these hydrothermal vents. Those hot, enriched, and dissolved nutrients. Hydrothermal vent plume. And so the other part you had to label was hot fluids carrying dissolved metals rise up through the crust. Okay? And this is supposed to be a video. It was a video. It's gone. Anyway, you can see it. So, and for some reason it's playing backwards. These, looks like it's sucking into the Earth. This is actually coming out, and this is a temperature probe from an ROV, a remotely operated vehicle, measuring temperature and possibly measuring or taking a sample of that plume for what dissolved nutrients are in there. And so this is adding salinity to the ocean, right? Okay, and now we're on 29, so we're filling in the rest of that, what I said before. Understand that the effects of hydrothermal vent plume can be detected some distance away from the vent site. So you've got these ROVs. It's actually an AUV, automatic one. It moves around by itself. It's programmed like a robot almost, and scans the surface with cameras, lasers, okay? And this is the result that it picks up. It picks up the temperature variations at different locations from the actual vent. And so it gives the hydrothermal temperature field and fluid flow all around the vent. So you don't actually have to go to a vent site to detect that it's there, is what we're trying to say. And I'm trying to say. And this is our last slide. So temperature near the seafloor is about not negative, that's approximately. That's an approximate sign. A little squiggly, not -2, that means it would be below freezing. And it hovers at just above freezing. So most things wouldn't be able to live down here in such cold water. But because of the hot water coming out, it makes this area right near it warm enough for 6'2" worms, crabs, fish, shrimp, mussels, all kinds of creatures, forming a little oasis in the bottom of the ocean around these hydrothermal vents, okay? But the water that comes out is very hot. I mean, approximately 300 to 400 degrees Celsius. And so, as the distance increases away from the vent, temperature decreases and there's no light, so you're not going to have any photosynthesis down here. You're going to have something called chemosynthesis, which we'll get to next time. Okay? And you can see, as this plume comes out, it rains down, particle fallout onto the surface, building up this little, it's not a volcano because it's not lava, it's just hot water with minerals in it. And those minerals form like the nutrients for the bacteria that live there that form the basis of the food chain. Okay? So those are your notes for part 1.